Welcome back. Today we will discuss some advanced problems of yield line theory. In the last class, we discussed the yield line theory application for the one-way continuous slab. So for that, it was quite simple as the yield line was a straight line, and we used the virtual load method as well as the equilibrium method for solving the collapse load. So the today's class is going to be little bit advanced. Why I'm telling advanced is that in the previous class you have seen that there are numerous possibilities of yield line formations. So for the case of inclined yield line, we need a simpler expression for finding the ultimate loads. So keep that in mind. Uh, we are going to resolve the moments for a better simplification. So I will go through these writings to make it very clear. So what we are going to do is that we have an inclined yield line, and we are going to represent the inclined yield line with respect to the horizontal and the vertical components, which will be easy to apply. So how to do that? Just a minute. Yeah. So the work done by the yield moment in the virtual work method of analysis, work done by bending and twisting moments acting along a yield line in going through rigid body rotation of the slab segment is required, for which general expression has been obtained in this section. Figure 20.9. This figure shows moment acting along the edges of a slab segment having E line of length L with horizontal and vertical projections Lx and Ly. So this inclined line is the yield line of length L, and the corresponding horizontal component is Lx, and the vertical component is the Ly. The slab undergoes a rigid body rotation whose components are theta x and theta y. So it's given here theta x and theta y. So we can see theta x, there are two arrow marks. That means that a rotation about this axis. So to make it more clear, yeah, just use pencil. And theta x means a rotation in this direction, that is perpendicular to this line, horizontal line, and the theta y will be the rotation which is perpendicular to the vertical line. So like this. Yeah. So coming back, so same thing is applicable to this empty also. This triangle, it will be in direction perpendicular to this direction. Okay, so we know what is theta x, theta y. It's direction of action, and mb and mt. So mb and mt. Mb is the bending moment which is making the twist at the yield line, and mt is the So that is like MB is the bending moment, and MT is the torsion moment, which will act like this. What I'm just showing in this direction. Yeah. So in this direction, and there the capacities MT and MB are the capacities along the E line. These moments shown in vector notation using the right hand thumb rule. The MX and MY, so MX is actually a moment about the vertical axis, and MY is the moment about horizontal axis, are the moment capacities per unit length along the horizontal axis, and my is along the vertical axis projections of the E line. So considering the equilibrium of the slab segment shown in figure 20.9, this one, we get that MB is the bending moment capacities along the E line is equal to mx sine square theta plus m by cos square theta, right? And from this equation, and we also know from this triangle calculations, we have mt is equal to mx minus my into sine theta cos theta based on the trigonometric calculations. So we got an expression of mb and mt, which is the bending and torsion moment on the E line, uh, with respect to the mx and my for the horizontal and the vertical axis. Then total absolute work done by mb and mt is equal to w is equal to mb into l. So this is a total moment into theta x cos theta plus theta y sin theta plus mt into L into minus theta x sin theta plus theta y cos theta. So by equating the equation number 20.4 and the previous equations, by putting the values of mb and mt what we obtained here into this equation, and after simplifying we will get w, the collapse load, is equal to mx into ly into theta y plus my into lx into theta x. So basically we converted, or we transformed the collapse load equation, which was based on mt and mp, into a very convenient mx and my with the help of ly theta y and lx theta x. That's the main equation we derived, and this is the work done by the moments mx into ly and my into ls acting on the horizontal and the vertical projections of the E line. The use of equation 20.5 will now simplify the calculations by eliminating the determination of MB, MT, and the corresponding rotations. So this is also important, the next one, nodal forces, which I will come back while we do the problem for circular slabs. So by the derived equation or the simplified form, now we are going to analyze the two-way slab. So we can read these things which are the informations regarding the bending of two-way slab. So I'll directly explain the problem. So for this two-way slab, there are two possible yield line. So in the last class we discussed the various yield lines can be there for the same condition, slab, say for the same slab condition. So here we are taking two yield line patterns. The yield line pattern one, which is based on not like based on, it is dividing the total slab into four segments of triangles. And I will just show the inline 2 also for a clear understanding. It is the 2 is based on triangles as well as the uh, trapezoidal shapes. Okay, so we need to find the collapse load for both conditions. So these are the most probable yield line behavior, and we want to check for which condition the value of collapse load will be less, and that will be the most critical one. Okay, we will analyze this one. So the okay, so the analysis of two-way slab. This was the conditions. One is and dividing the entire thing into triangular segments, and second one was triangular plus trapezoidal segments. So we just read it out. Figure 18.12. Previously, it shows the different E-line pattern for two-way rectangular slab, and in our case, first case, the total slab is divided into four segments: one, two, three, and four. And the tree ball diagrams of the different segments are given here. So one thing to note is that the 1 and 3 are identical and 2 and 4 are identical. So we need to find only for either 1 or 3 and 2 and 4, and we can multiply by the 2. Okay, then the other important things include the let the vertical deflection at the intersection of the line be delta. So at this point, total vertical deflection will be delta, and therefore the deflection at the centroid of each triangle will be delta by 3. So the we are dividing this in triangle, and at the centroid deflection will be one third of the deflection at the midpoint. So it will be delta by 3. So please remember that for the last case, we had delta by 2. I'll just show it fast. Yeah, this was the case. So this one was delta, and being a single slope, the value will be delta by 2 at the centroid, right? And for this case, being the four triangles, and for each triangle the centroidal deflection is equal to delta by 3. So we resolved. I'll just maximize this for a clear understanding. Yeah. So please note that the given slab condition is fixed throughout the support, so that there is a formation of the negative yield line through the entire support here, and there are the positive yield lines which are diagonal, and the Lx Ly is given, and the freeboard diagram. So 3 and the 4 is given. As I told, we can analyze for 3 and 4 and multiply by 2 to get the entire behavior. Okay, so we will try to analyze the two or the slab by two methods. One is the equilibrium method, and the first one the virtual load method. So the slab will be analyzed by both the methods, the virtual work method and the equilibrium method. In the case of virtual work method, we have total work done. So we know that we are applying a UDL load W, and so W into Lx into Ly will be the area of the entire slab into delta by 3 will give you the total external work done. So the total external work done EWD by the ultimate uniformly distributed load is given by W into Lx into Ly into delta by 3, and the total internal work done IWD by the yield moments is given by IWD is equal to 2 into m 2 into mn by lx theta y. So we have the 4 1 2 3 and 4. So you see IWD is equal to 2 into mn by lx into theta y plus 2 into mnx. So what are these mny, mnx and mpy? So let's see this freeboard diagram, the third segment, and the actually these are the inclined yield line, and we have Lx here, Ly here, and Mny is the moment in the direction of x, Mny, and this is Mpx, and we have Mpy in the in this direction, and there is Mpx also. So we have Mpx, Mps, and Mpy, Mpy. Then this is the Mny. And for the fourth segment, we have Nx at the end or the support side, and the other thing are Mpy and Mpy here, and Mpx and Mpx at this side also. So the ny is ny is normal one is always parallel to the support direction, and the mpx and mpy uh, are the non-parallel sides in the segment considered. Okay, so coming back to the total work done is equal to, so take the first FBD. Then for that case, 2 into mny into lx into theta y. So we are taking the twice value because we have the 3 and 1 identical. So this 2 is for multiplying for two segments. So mny into lx into theta y plus mnx. Yeah, so we have we are first using the normal values, that is uh, on the supports. So the mny was used mny into lx into theta y plus 2 into mnx into ly into theta x plus, then comes the 2 mp in my sorry 2 mpy into lx into theta y plus 2 into mpx into ly into theta x. So these values, we the mpy values and the mpx values. So those values are used to find the total internal work done by the yield moments, and by equating the external work done with the total internal work done, by equating these two equations we can, or we'll get, after simplification, W is equal to 21 into mnx plus mpx by lx square plus mny plus mpy by ly square. So this will be the solution based on the virtual work method. So next one is actually the equilibrium method. So we know that equilibrium method is based on the static equilibrium, and for the first case, let's consider the equilibrium of segment 3 and take moment of all the forces about its lower edge. So we are going to take the moment of all this thing about this lower edge. So that will be equal to half into W Lx into Ly by 2 into Ly by 6. So it's based on the load acting on the surface, the total triangle area into the lever arm will give you the first part of this equation plus V into Ly by 2. So that V is the shear force into Ly. Ly by 2 will be the lever arm. So this Ly by 2 minus mny into Lx minus mny into Lx will give you the uh, moment about this base, then minus mpy into Lx. So mpy we have into x. So note that the there are some positive, that means clockwise moments as well as the anti-clockwise moments that are that's why but there is some negative signs coming for mny and mpy for the first equation. Yeah. So the first equation, similarly, let's consider the equilibrium of segment 4 and take the moment of all the forces about this left edge. So next one we are going to take the moment about this edge, and so the first part is on the moment due to the applied loading, then the shear force for consider the equilibrium, and then the mnx and mpx values, mpy and the mpx values. So by equating like this and by solving the equations, we will get the W as 12 into mnx plus mpx by lx square plus mny plus mpy by ly square. So that is similar to the one of virtual work method, and there are some two conditions, special conditions of simple supported slab means simple support square slab means Lx Ly will be equal to L, and there won't be any Mn as it's simply supported, there won't be any fixed moments or the hogging moments at the end, which is denoted by the Mny and Mnx. So that will be 0, and mpx is equal to mpy is equal to m0. So substituting those values in this equation will give the bending moment is equal to W into L square by 24. Then case 2, for a square slab with all edges fixed. Square slab means Lx Ly will be equal to L and all edges fixed. So there will be some moment of M Nx and M Ny. Support moments are equal to those of the central span. The collapse load can be obtained using the equation 20.7. So this equation can be used to find the collapse load for the special cases. So the same way, like we did for the first line pattern, we can now we can discuss regarding the line pattern 2, which is like this. The same thing of all edges fixed, and the E line divides the total slab into four segments: one, two, three, and 4. And in this case, actually, the we are not known regarding the x distance at which the fourth segment joins the total uh, E line. Okay, so the important terms in this one, this figure includes the negative E line around all the supporting edges, and positive E lines are there inside the slab, and x is unknown to us, and Lx is the total length of slab, and Ly is the width of the slab. And by we are taking only the segment 3 and 4, considering the 1 and 3 are identical, and 4 and 2 are identical, and we are dividing the trapezium into three segments of two triangles and one rectangle. So the free body diagram looks like this, and MNY is a fixed end moment at this support, and 3A, 3B, 3C. MPX and MPX are there on the both sides, and we have MPY perpendicular to the MPX. So this gives the FPD diagram, and the same for or similar for the four segment also we have the fixed end here. So MNX, and we have uh, MPY horizontal values of moments, and MPX always vertical. So this constitutes the E-line pattern 2, and here the things required for calculation include the analysis of slab. The slab will now be analyzed by both the methods of virtual work method and the equilibrium method. In the case of virtual work method, total external work done by the uniformly distributed load is given by, so we have divided the entire slab into actually four segments, two identical, and is equal to 2 into work done by 3A. So this is 3A, 3B, 3C. So 2 times work will be equal to 3A equal to 1A, 3B equal to 1B, 3C equal to 1C. So 2 times work by 3A, 2 times work by 3B, 3C plus 2 times work by 4 will give you the total work done. And so 2 into work done is equal to half into Wx into Ly by 2. So that means that this is the area of this segment. So Wx into half into Wx into, sorry, half into W into X is the base, and Ly by 2 is the altitude, which which gives the first part. 2 into half into Wx into Ly by 2 into delta by 3, taking from the centroid, plus 2 into W into Lx minus 2x. So we know this distance from the free end, sorry, this support end to here is x. Similar for the right side also, to x plus x 2x. So we are deducting from the lx to get the width of this rectangle. So total lx minus 2x into ly by 2 will give you the area of the 3b. Yeah, that is shown here in delta by 2, as it is a rectangle centroid at the half point. Delta by 2 plus again the repetition of the first, so w3a is equal to w3c. So again the repetition plus the load of w4, 2 into 1 by third, 2 into, so this area of this triangle and the corresponding centroid delta by 2 will give you w into delta by 6 into 3lx into ly minus 2x into ly. So we found the total external work done by dividing the total slab into different segments. The total internal work done is given by the same segments, 2 into m ny into lx into theta y plus 2 m nx into ly into theta x plus so this is actually m ny will be the m ny is the fixed end moment in, which is fixed end moment in the uh, direction of lx about hlx, okay, about the lx. And similarly the ny, sorry, nx is actually uh, about the verticals, about the verticals, as there is double triangle shown. So by using these values and internal work done, it is given or it's obtained by using the equations. And once we equate the external work done to internal work done, we will get w is equal to a long equation. And this, we were telling that some mathematical calculations coming into picture now. We want to differentiate this equation for a, with respect to x, to find the lowest value of x. So once we differentiate it, we'll get a quadratic equation in x. So based on the questions, we can analyze for the for this analyze this equation, find the required values. The equilibrium method, the same thing like we did for the previous one. Let us consider the equilibrium of slab segment 3 and taking moment of all about lower edge. So I'm not repeating again. So this third segment taking the moment about this horizontal, and fourth one taking moment about this vertical will give you the value of w is equal to 24 into mpy plus mny into lx by 2x into ly square plus 3 into ly square into lx minus 2x. Similarly, considering the fourth segment, we will get another w. Equating the two expressions of w, we will get the same expressions as in uh, the previous one. Now, mm, for this is the expression of 20.9a. Okay, so it was like the previous expression. And here we have for x is equal to lx by 2, that is S is equal to Ls by 2 means we know that Ls is equal to the total length. Ls by 2 means a center point. That means it will be equal to a division of four not equal four triangles. For that condition, like for the previous one, will give you an expression like this. If the condition is satisfied, for this condition, if all the yield lines are meeting at the midpoint, then it will exhibit an yield pattern of 1, and if x is less than Lx by 2, it can be shown that this will be the condition. So this is the values we got from the analysis. So we will try to solve a problem to make the understanding better. Find the collapse load for a 6 meter by 4.5 meter rectangular slab fixed all edges, for which the midspan moment is 80% of the support moment in the corresponding direction. The moment in the longer direction is 40% of that in shorter. So these are the given parameters. So mpy is equal to zero point 0.8 into mny. So midspan moment mpy is equal to 0.80 support moment mny is equal to m, and mpx is equal to 0.8 into mns is equal to 0.4. It's given that it is 40% in the shorter direction. So Lx is equal to 6 meter, Ly is 4.5 meter. So we want to first check for which pattern for which yield pattern the slab will break. For yield pattern 1 we have the condition, for yield pattern 2 we have the condition here, and once we calculate the values by this, we will get that the value will be for the left side value will be zero point 0.4 and right side value will be 1.78. That means that the values less will be applicable and the yield pattern 2 will prevail. And for that case we can use the equation which we derived for the second condition of inline 2, and so that we can find the ultimate load. So there is one more problem in this one that we can refer as a homework. So I will give you this PDF for reference. This is actually for a rectangular slab simply supported three edges and free at the other. So this is actually divided into three segments: one pure triangle, one you can cut into a triangle and a rectangle as shown here, 3A 3B. Then you want to draw the freeboard diagrams, and then you can find the collapse load by virtual work method as well as the equilibrium method. And there is a chance of one more E line in addition to this, that is given here as the second E-line pattern. So this also we can analyze by the FBD diagram for the virtual work method and the equilibrium method, and we can solve for the equation. And there is a problem also given for the above condition which you can analyze now. Yeah. So that's the expressions or equations which are available for solving the rectangular slabs for one-way condition and the two-way conditions. So I'll stop for today. Thank you.